Hi, in this video we'll examine the motion of a star around a black hole and use the star's position during orbit to determine its net force, as well as the net force's parallel and perpendicular components. We will also use variables yielded from our analysis to solve for the mass of the black hole, using the formula for gravitational force between the star and the black hole. We'll start with our given information. The mass of the star was given to be 1.9890 e to the 30th kilograms, and we are told that the time period for the star's orbit was 1 Earth day, or 86,400 seconds. The position of the black hole was given to be 4 e to the 10th meters in the x direction and negative 1 e to the 10th meters in the y direction, and we are given all the position points for the star during orbit, some 10,000 points. We'll use these to calculate the changing velocity of the star, which will yield us a rate of change in momentum, which will yield the net force of the star. But first, we'll begin with Newton's second law, recognizing that net force is equal to change in momentum over delta t, or dp dt, which we'll use in our VPython code later. We should note, though, that while the rate of change in momentum is equal to the net force, they are different, and that net force and its components are external causes acting on an object, whereas the change of momentum is a property of the object, its mass and velocity over time. In other words, the change in momentum is caused by the net force. As you can see, we broke the star's net force into parallel and perpendicular components. We can then sum these components to equal the total net force acting on the star, shown here. By plugging in the positions of both the black hole and the points from the star, as well as the mass of the star, into VPython, we can, at least in theory, show the net force vectors, total, parallel, and perpendicular, acting on the star. As you can see here, my code is not functional, despite multiple deletion of star position points and tweaking of formulas. However, if the VPython code did work, it would show a perpendicular net force represented by the blue arrow pointing inward toward where the black hole would be, and the parallel net force component represented by a black arrow changing with the star's orbit. The total net force vector is shown as the yellow arrow. Despite the arrows glitching and not moving, the code actually did calculate these components, shown here, with the total net force being equal to 3.60606 e to the 26 newtons, and the parallel net force being equal to 1.3534 e to the 26 newtons, and the perpendicular net force component being equal to 2.7455 e to the 26 newtons. We can use the net force found in VPython to solve for the mass of the black hole by recognizing that the only force acting on the star is the gravitational pull between the star and the black hole, and setting that equal to the net force. We can then isolate the mass of the black hole variable in order to solve for it, shown here. The position of the star used was the first one shown in our star position spreadsheet. Upon plugging in the values shown, we get that the mass of the black hole was equal to 2.0307 e to the 31st kilograms. It should be noted that if a different black hole was in place instead of this one, a black hole of a different mass, then the net force acting on the star would be different, even with the positions of the star and black hole remaining the same.